Hello and welcome to this tutorial on how to operate the Pooleys CRP-5 navigation computer. The computer is an arrangement of fixed and rotating discs and a two-sided sliding scale. It can be used to solve the often complex calculations required for navigation and flight planning. Before we start, it's important to be aware of two things about the answers we get from the CRP-5. Firstly, we need to gross error check the magnitude of the answer. For example, the figure 12 could represent 1.2, 12, 120, 1,200 and so on. Secondly, it's important to remember that the CRP-5 is a circular slide rule. The answers it provides are not as precise as those you would get from an electronic calculator. They are close approximations only, but are good enough for the purposes we need them for. We will start with a look at the parts of the CRP-5. On the calculator side, there is a fixed outer scale, a rotating inner scale, and a rotating cursor. You will also notice that there are 4 windows cut out of the inner rotating disc. These are the Airspeed window, the altitude window, the density altitude window, and the compressibility correction window. We'll look at the function of each of these windows later in the tutorial. The blue scale on the rotating inner scale is called the temperature rise scale and is used for calculating the effect of speed on temperature. This scale is often referred to as the RAM rise scale, and again we will look at its function later in the tutorial. Now let's look at the other side of the computer. Again, it has 3 parts: a fixed outer scale, a rotating inner scale, and a sliding wind scale. Altimeters are calibrated to the International Standard Atmosphere, which we call ISA. If the temperature is not the same as the ISA temperature for the altitude you are flying at, then there will be a difference between the altitude shown on your multimeter and your true altitude. We will now show you how to convert between indicated and true altitude on the CRP-5. An aircraft is flying at flight level 220, where the outside air temperature is minus 40 degrees centigrade. The QNH is 1013 hectopascals. What is the true altitude being flown? To answer the question in this example, we take the following steps. In the altitude window, align the pressure altitude of 22,000 feet on the outside of the window with the outside air temperature of minus 40 degrees centigrade inside the window. Then look up the indicated altitude of 22,000 feet on the inner scale and read off the true altitude of 21,000 feet on the outer scale. Note that when the QNH is the same as the standard pressure setting of 1013 hectopascals, the indicated altitude and the pressure altitude will be equal. An aircraft is flying at a pressure altitude of 16,000 feet, where the outside air temperature plus 15 degrees centigrade and an indicated altitude of 15,000 feet. What true altitude is being flown? Firstly, in the altitude window, align the pressure altitude of 16,000 feet on the outside of the window with the outside air temperature of plus 15 degrees centigrade inside the window. Next, look up the indicated altitude of 15,000 feet on the inner scale and read off the true altitude of 16,900 feet on the outer scale. Aircraft usually fly at altitudes and flight levels based on atmospheric pressure. For some performance calculations, however, we need to know the density altitude. Density altitude, which can be calculated on the CRP-5, is defined as the altitude in the standard atmosphere to which the actual air density corresponds. Now we will look at using the CRP-5 to compute density altitude. What is the density altitude of an airfield with an elevation of 3,000 feet above mean sea level, where the temperature is +9 degrees centigrade? This time, we will be using the airspeed window. First, align the elevation of 3,000 feet inside the window with the temperature of +9 degrees centigrade outside the window. Now go to the density altitude window and read off the density altitude against the black arrow. You will see that the density altitude is 3,000 feet, the same as the airfield elevation. This is because the temperature at the airfield is equal to the ISA temperature. Now let's look at an example where the temperature differs from the ISA temperature. What is the density altitude at an airfield with an elevation of 3,000 feet and a surface temperature of +25 degrees centigrade? Firstly, in the airspeed window, align the elevation of 3,000 feet inside the window with the temperature of +25 degrees centigrade outside the window. Then go to the density altitude window and read off the density altitude of 5,000 feet at the black arrow. An aircraft's speed through the air can be described in several ways depending on which error factors we wish to take into account and for what purpose we need the figures. The possible errors we may wish to take into account include instrument error, position error, pressure error, density error and compressibility error. The speeds we may need include indicated airspeed, rectified or calibrated airspeed, equivalent airspeed, true airspeed, Mach number. The calculation of flight limitations might require the equivalent airspeed or Mach number, whilst flight performance data and navigation calculations require the true airspeed. We can convert directly between various airspeeds using the CRP-5. Rectified airspeed and calibrated airspeed are effectively the same thing. We shall use the term rectified airspeed in this tutorial. In this section, we will see how to calculate a true airspeed from a rectified airspeed and also a rectified airspeed from a true airspeed. The true airspeed is defined as the speed of the aircraft relative to the air mass in which it is. It is the rectified airspeed adjusted for changes in pressure and density caused by altitude and temperature. The airspeed indicator in the aircraft shows indicated airspeed. Before we convert this to true airspeed, it must be converted to rectified airspeed to allow for the instrument and position errors caused by the design and operation of the sensing system. However, the difference between indicated airspeed and rectified airspeed is so small that we can ignore them for the purpose of our calculations on the CRP-5. In this example, we wish to calculate the true airspeed of an aircraft flying at a rectified airspeed of 150 knots at flight level 120, where the temperature is -5 degrees centigrade. Firstly, we go to the airspeed window. Then we align the temperature of -5 degrees centigrade outside the window with 12,000 feet pressure altitude inside the window. We look up 150 knots on the inner scale and read off the corresponding true airspeed of 181 knots on the outer scale. In the next two examples, we will look at correcting our computed true airspeed for compressibility when the true airspeed value exceeds 300 knots. Using the CRP-5, we need to calculate the true airspeed of an aircraft flying at a rectified airspeed of 280 knots at flight level 290, where the temperature is -40 degrees centigrade. Firstly, locate the airspeed window. Align the temperature of -40 degrees centigrade outside the window with the pressure altitude of 29,000 feet inside the window. Look up the known rectified airspeed of 280 knots on the inner scale and read off the true airspeed of 444 knots on the outer scale. Because this true airspeed is greater than 300 knots, we must correct it for compressibility. To do this, we locate the window marked Comp Core and apply the formula printed next to the window to the uncorrected true airspeed we have just found. So 444 divided by 100 is 4.44, minus 3 gives us 1.44. Now we rotate the inner scale counterclockwise in the direction of the arrow by 1.44 divisions. We again look up the known rectified airspeed of 280 knots on the inner scale and read off the corrected true airspeed of 431 knots on the outer scale. In this example, we need to calculate the rectified airspeed of an aircraft flying at true airspeed of 550 knots at flight level 320, where the temperature is minus 50 degrees centigrade. In the airspeed window, align the temperature of minus 50 degrees centigrade outside the window with the pressure altitude of 32,000 feet inside the window. Look up the true airspeed of 550 knots on the outer scale and read off the rectified airspeed of 332 knots on the inner scale. As in the previous example, the true airspeed is greater than 300 knots, and so we must correct for compressibility. To do this, we locate the window marked Comp Core and apply the formula printed next to the window to the uncorrected true airspeed. So, 550 divided by 100 is 5.5, minus 3 gives us 2.5. Move the vertical pointer in the Comp Core window 2.5 divisions to the left in the direction of the horizontal arrow. It is important to note that whether you are converting rectified airspeed to true airspeed or true airspeed to rectified airspeed, the pointer is always moved to the left. Again, look up the true airspeed of 550 knots on the outer scale, and this time read off the corrected rectified airspeed of 347 knots on the inner scale. In the last section, we learnt how to use the CRP-5 to calculate rectified and true airspeeds. Now we will learn how to use it to calculate a Mach number from a true airspeed and a true airspeed from a Mach number. The Mach number is a figure that shows the speed of an aircraft as a ratio of the aircraft's speed to the local speed of sound in the surrounding air. The local speed of sound varies according to the ambient air temperature, and if the aircraft's speed and the local speed of sound are the same, then the aircraft speed is Mach 1. In this example, we will calculate the Mach number of an aircraft flying at a true airspeed of 453 knots at flight level 330, where the temperature is minus 45 degrees centigrade. Firstly, we move the airspeed window until it is below the 10 on the outer scale to bring the Mach number index into view. Then we align the temperature of minus 45 degrees centigrade outside the window with the Mach number index inside the window. Look up the true airspeed of 453 knots on the outer scale and read off the Mach number of 0.77 on the inner scale. In this example, we need to calculate the true airspeed of an aircraft flying at Mach 0.82 at flight level 310, where the temperature is minus 55 degrees centigrade. Firstly, we turn the airspeed window to reveal the Mach number index. Then align the temperature of minus 55 degrees centigrade outside the window with the index. Now look up the Mach number of 0.82 on the inner scale and read off the true airspeed of 471 knots on the outer scale. In this example, we have to calculate the Mach number of an aircraft flying at a rectified airspeed of 280 knots at flight level 380 in ISA conditions. We do this in two stages. Firstly, solving for true airspeed. In the airspeed window, we align the ISA temperature of minus 56.5 degrees centigrade with the pressure altitude of 38,000 feet. Then we look up the rectified airspeed of 280 knots on the inner scale and read off the true airspeed of 525 knots on the outer scale. This value exceeds 300 knots, and so we have to correct the figure for compressibility. First, we use the uncorrected true airspeed of 525 knots in the formula printed next to the comp core window. This gives an answer of 2.25. We move the vertical pointer 2.25 divisions to the left. Now we look up the rectified airspeed of 280 knots on the inner scale and read off the corrected true airspeed of 500 knots on the outer scale. The second stage is to solve for Mach number. We move the airspeed window to reveal the Mach number index and align the ISA temperature of minus 56.5 degrees centigrade on the outside of the window with the index. Now we look up our corrected true airspeed of 500 knots on the outer scale and read the Mach number of 0.87 on the inner scale. Heating caused by compression of the air, anti-icing devices and friction effects cause sensing errors in the electronic thermometers installed on many aircraft. As a result of these errors, the temperature indicated, known as the total air temperature, will be higher than the real or static air temperature. Total air temperature is sometimes called RAM air temperature. Static air temperature is also known as corrected outside air temperature, or just outside air temperature. To get the static air temperature from the total air temperature, we need to apply a negative correction. This correction varies with the true airspeed of the aircraft. The correction also varies between different thermometer systems. The amount of the correction will be related to what is known as the recovery factor of the system. On most commercial air transport and business aircraft, the correction is calculated by the air data computer. However, the differences in recovery factor between different systems in different aircraft are small enough to allow us to use the CRP-5 to make approximate conversions between total air temperature and static air temperature. Let us say that the indicated total air temperature at 460 knots true airspeed is minus 25 degrees centigrade. We will use the CRP-5 to find the corresponding static air temperature. To find the temperature, we must subtract from the total air temperature to get the static air temperature. We use the blue temperature rise scale on the inner movable ring. Look up 460 knots true airspeed on the outer knots scale in the blue area and read off the temperature correction of 23 degrees centigrade on the inner scale. The static air temperature is always less than the total air temperature, so the 23 degrees must be subtracted from the indicated total air temperature. This gives us minus 25 degrees centigrade less 23 degrees centigrade, which is minus 48 degrees centigrade. We can use the CRP-5 to convert one type of unit of distance to another. The units include nautical miles, statute miles, yards, feet, kilometres and metres. In practice, the most frequently used conversions tend to be between nautical miles, statute miles and kilometres. When performing conversions between nautical miles, statute miles and kilometres, note that the alignment position for the kilometres, metres, litres index is on the outer scale at the top 12 o'clock position on the CRP-5, directly beneath the blue 10. And that the alignment point for the nautical miles index is in the left 9 o'clock position, directly above the mark representing the number 54. Don't confuse the nautical mile index with the statute mile index. The statute mile alignment point is in the left 10 o'clock position, directly above the mark representing the number 62. Now let's look at a couple of examples. To convert 240 nautical miles into kilometres, we align 240 on the inner scale with the nautical miles index. Then go to the kilometres, metres, litres index on the outer scale and read off the answer of 444 kilometres on the inner scale. To convert 600 kilometres to nautical miles, align 600 on the inner scale with the kilometres, metres, litres index. Then, look up the nautical miles index on the outer scale and read off the answer of 324 nautical miles on the inner scale. It is worth noting that you could also read off 373 statute miles against the statute miles index. In this example, we are told that an aircraft flies 240 nautical miles in 1 hour and are asked how many kilometres it will fly in 2 hours. We align 240 on the inner scale with the nautical mile index on the outer scale and read off 444 kilometres on the inner scale against the kilometre, metre, litre index on the outer scale. This is the distance flown in 1 hour, so we need to multiply it by 2 to get the answer of 888 kilometres. To find how many nautical miles an aircraft flies in 3 hours if it flies 820 kilometres in 1 hour, we first align 820 on the inner scale with the kilometre, metre, litre index on the outer scale. Then we look up the nautical mile index on the outer scale and read off 440 nautical miles on the inner scale. This is the distance flown in 1 hour, so we need to multiply it by 3 to get the answer of 1,332 nautical miles. In this example, we need to convert 14.5 nautical miles to feet. We align 14.5 on the inner scale with the nautical mile index on the outer scale, and then against the feet index mark on the outer scale, we read off 88,000 feet on the inner scale. The CRP-5 shows 8.8 as the answer, and a quick mental calculation is needed to determine the magnitude of the answer. We know that a nautical mile is 6,080 feet, so a distance greater than or than 60,800 feet. Hence the answer must be 88,000 feet. And finally in this section, we will work out the aircraft speed in knots, given that it travels 1,520 kilometres in 2.5 hours. Align 1,520 on the inner scale with the kilometre, metre, litre index on the outer scale. Now go to the nautical mile index on the outer scale and read off 820 nautical miles on the inner scale. This is the distance flown in 2.5 hours, so we need to divide it by 2.5 to get the answer of 328 knots. The CRP-5 can be used to solve distance, speed and time problems using the outer scale to represent both distance and speed and the inner scale to represent time. As shown here, the distances we use are usually ground distances, and so the speeds we use or calculate are ground speeds. You will note that the moving inner scale comprises 2 scales, a white outer scale calibrated in minutes and a yellow inner scale calibrated in hours and minutes. In this first example, we will calculate how long it will take to fly a distance of 135 nautical miles at a ground speed of 478 knots. First of all, we align the black triangle on the inner scale, sometimes known as the 1 in 60 index, and which is effectively equal to 60 minutes, with the distance of 478 nautical miles on the outer scale. This means that the aircraft will cover 478 nautical miles in 60 minutes. Now look up 135 nautical miles on the outer scale and read across to 17 minutes on the inner scale. Therefore, it will take approximately 17 minutes to fly 135 nautical miles. Here we will look at the case where we know the ground speed of 320 knots and need to know how far we will fly in 15 minutes. This time, we align the black 1 in 60 triangle on the inner scale with 320 knots on the outer scale. This means that the aircraft will cover 320 nautical miles in 60 minutes. Now we can look up 15 minutes on the inner scale and see that it corresponds to 80 nautical miles on the outer scale. This is the distance the aircraft will fly in 15 minutes. Lastly, if we know that an aircraft flies 120 nautical miles in 36 minutes, we can find the ground speed. We start by aligning 36 minutes on the inner scale with 120 nautical miles on the outer scale. Now we simply go to the black 1 in 60 triangle on the inner scale and read off the ground speed of 200 knots on the outer scale. The CRP-5 can be used to convert between different units of fuel volume, such as imperial gallons, United States gallons and litres. Also, using the known specific gravity of the fuel weight in pounds or kilograms can be calculated. As always, when reading an answer from the CRP-5, we must have an idea of the order of magnitude we are expecting. For example, does 6 represent 0.6, 6, 60, 600, 6,000, or 60,000? It is useful to know that 1 imperial gallon is equal to 1.2 United States gallons, and also to 4.55 litres. Water has a specific gravity of 1, which means that 1 gallon of water weighs 10 pounds and 1 litre weighs 1 kilogram. For example, 1 imperial gallon of fuel with a specific gravity of 0.8 weighs 8 pounds, whilst 1 United States gallon of the same fuel weighs 6.7 pounds. 1 litre of water weighs 1 kilogram, but a litre of fuel with a specific gravity of 0.8 weighs only 0.8 of a kilogram. In our first example in this section, we need to find the weight in kilograms of 1,000 imperial gallons of fuel with a specific gravity of 0.8. Looking first at the magnitude of the answer we are expecting, we know that there are 4.55 litres in an imperial gallon, and that this would weigh about 3.6 kilograms at 0.8 specific gravity. So, we are looking for an answer in the region of 3,600. To be more precise, we first locate the imperial gallon index on the outer scale. Align 1,000, using the blue 10 on the inner scale, with the imperial gallon index on the outer scale. Up 0.8, use 80. Read off the inner scale a value of 3.635. We know that this must represent the answer of 3,635 kilograms. In our first example in this section, we need to find the weight in kilograms of 1,000 imperial gallons of fuel with a specific gravity of 0.8. Looking first at the magnitude of the answer we are expecting, we know that there are 4.55 litres in an imperial gallon, and that this would weigh about 3.6 kilograms at 0.8 specific gravity. So, we are looking for an answer in the region of 3,600. To be more precise, we first locate the imperial gallon index on the outer scale. Align 1,000, using the blue 10 on the inner scale, with the imperial gallon index on the outer scale. Up 0.8, use 80. Read off the inner scale a value of 3.635. We know that this must represent the answer of 3,635 kilograms. Now let's work out how many litres are in 1,000 pounds of fuel with a specific gravity of 0.8. First, align 1,000, using the blue 10 on the inner scale, with 0.8, use 80, on the specific gravity, pounds, scale on the outer scale. Then look up the kilometre, metre, litre scale on the outer scale and read off 568 on the inner scale. This gives the answer that 1,000 pounds of fuel with a specific gravity of 0.8 has a volume of 568 litres. To find the weight in kilograms of 280 litres of fuel with a specific gravity of 0.78, we first align 280 on the inner scale with the kilometre, metre, litre index mark on the outer scale. Then we look up 0.78 on the specific gravity, kilogram scale on the outer scale, and read off 218 on the inner scale. This gives us our answer of 218 kilograms. Now let's look at some examples of computing fuel consumption in terms of weight burnt in a certain time. If an aircraft has used 1,800 pounds of fuel in 23 minutes, what is the fuel flow in pounds per hour? Line up 23, representing minutes, on the inner scale with 1,800, representing pounds, on the outer scale. Go to the black 1 in 60 triangle on the inner scale and read off the figure 4,700 on the outer scale. This indicates a fuel flow of 4,700 pounds per hour. Now we are given the fuel flow of 85 kilograms per hour and asked to calculate how much fuel will be used in 2 hours and 40 minutes. Align the black 1 in 60 triangle on the inner scale with 85, representing 85 kilograms per hour, on the outer scale. Go to the inner yellow time scale and locate the mark for 2 hours and 40 minutes. Line up the cursor line with this mark and read off the outer scale the value of 226. This is the number of kilograms of fuel that will be used in the 2 hours 40 minutes. If we know that an aircraft is using 6,200 pounds of fuel in an hour and it has a ground speed of 420 knots, we can use the CRP-5 to determine its fuel consumption in pounds per nautical mile. This is an example of the use of the computer to solve a division problem. First, locate 420 on the inner scale and 6,200 on the outer scale and align the two figures. You now have 6,200 over 420. Now look up the blue 10 on the inner scale and read off the figure of 14.75 on the outer scale. This represents the result of dividing 6,200 by 420 and gives us the number of pounds of fuel used per nautical mile. In aviation, the line we fly between 2 points is usually a straight line known as the course or track line. In still air, we would maintain that course by simply pointing the aircraft in that direction. In most cases, however, the wind will try to blow the aircraft off course, and we will need to counteract its effect by turning into it. By calculating accurately the effect of the wind, we will know how much to turn into it to keep our aircraft on course. We have already seen how to calculate one type or measure of airspeed from another. We use the ground speed to calculate our progress along the course or track line. Our airspeed indicator shows our indicated airspeed, which to all intents and purposes is the same as the calibrated airspeed. We can calculate our true airspeed from the calibrated airspeed. Throughout the following examples, we will use the abbreviations shown here. It is worth noting that WV is for wind vector and not for wind velocity. The wind vector is made up of the wind direction and the wind speed and is presented, for example, as 210 diagonal 20. This means that the wind is coming from a direction of 210 degrees at a speed of 20 knots. We require different types of calculation for different phases of flight. We might need to calculate drift and ground speed given heading, true airspeed and the wind vector. Track and ground speed given heading, true airspeed and the wind vector. Heading and ground speed given track, true airspeed and the wind vector. The wind vector given true airspeed, ground speed, heading and track. We will also look at calculating a wind vector from two drift lines. Now let's look at each of these in turn. Let's first take a look at calculating the drift and ground speed if we have the true airspeed, the heading, and the wind vector. In this example, we are asked to calculate the ground speed and drift experienced by an aircraft flying at a true airspeed of 140 knots on a heading of 080 degrees true with a wind vector of 120 degrees at 20 knots. Selecting the low speed side of the sliding wind scale, we align the wind direction of 120 degrees true on the inner scale with the true heading index on the outer scale and slide the scale so that the true airspeed of 140 knots is below the centre dot. Now, we count down the wind speed of 20 knots below the centre dot, taking us to the 120 knot mark, and make a small wind mark on the computer. Now, align the heading of 080 true on the inner scale with the true heading index. You will see that the wind mark has now moved to the left side of the wind computer's centre line. You can now see that the wind mark is 6 vertical drift lines to the left of the centre dot and over the 126 knot speed line. Therefore, on this heading, the wind has given us 6 degrees of left drift and a ground speed of 126 knots. Now we'll have a look at calculating our track and ground speed if we know our heading, true airspeed and the wind vector. We do this by applying the drift we've calculated to the heading, adding it or subtracting it as appropriate. In this example, we are asked to calculate the track and ground speed of an aircraft flying at a true airspeed of 220 knots on a heading of 150 degrees true with a wind vector of 280 at 40 knots. Selecting the low speed side of the sliding wind scale, we first place the centre dot over the true airspeed of 220 knots and align the wind direction of 280 degrees. Now we count 40 knots down from the centre dot over the true airspeed and make a small wind mark on the computer above 180 knots. This represents the wind speed of 40 knots. Now move the inner scale to align the heading of 150 true with the true heading index. Note that the wind mark has moved to the left side of the wind computer centre line. Read off the values of 7 degrees left drift and a ground speed of 248 knots under the wind mark. Finally, look at the wind computer outer drift scale and read off the track on the inner scale under 7 degrees left on the outer scale. We always apply the drift from heading to track. So now we have the answer of a track of 143 degrees true and a ground speed of 248 knots. Now let's look at calculating the heading and ground speed when we know the track, true airspeed and the wind vector. In solving these problems, we may need to apply a sequence of initially coarse and progressively finer corrections to arrive at our final answer. In this example, we have a true airspeed of 200 knots, a track of 160 degrees true, and a wind vector of 230 degrees at 50 knots, and we wish to calculate the heading and ground speed. Selecting the low speed side of the sliding wind scale, we first put the true airspeed of 200 knots underneath the centre dot. Then align the wind direction of 230 degrees true on the inner scale with the true heading index on the outer scale. Now count down the wind speed of 50 knots below the centre dot and make a small wind mark on the wind computer above 150 knots. Now align the track of 160 degrees true on the inner scale with the true heading index on the outer scale, and note that your wind mark has moved to the left-hand side of the wind computer. By counting the vertical lines to the left of the centre dot, we can see that the wind mark is sitting on 14 left drift. We now start the computation process by locating the drift values on the outer scale of the wind computer and initially aligning the track of 160 degrees true on the inner scale with 14 left drift on this outer scale. When we have done this, we see that the wind mark has now moved to overhead the 13 left drift line. We therefore now align the 160 track value on the inner scale with 13 left drift on the outer scale, and we see that the wind mark is still over the 13 left drift mark. Because the drift on the sliding wind scale and that on the top outer drift scale are the same at 13 left drift, the computation is now complete. We can now read off the heading of 173 degrees true under the true heading index and the ground speed of 178 knots under the wind mark. We can calculate the wind vector if we know the true airspeed, the ground speed, the heading and the track. In effect, we are resolving the triangle of velocities. In this diagram, we are flying along a track between A and B. If there were no wind, the aircraft's heading would be the same as its track over the ground. But if there is a wind, we must allow for its effect by heading into it, and so the aircraft's heading and track over the ground will be different. At this point, it is worth noting that in some exam questions, the track may be referred to as course. They are the same thing. Occasionally, you will need to carry out additional calculations to find one or more of the four components before using the CRP-5 to calculate the wind vector. For example, you might need to find the true airspeed when given a Mach number and temperature. In our first example, we need to calculate the wind vector from the information given at the top of the slide. Selecting the low speed side of the sliding wind scale, we first position the centre dot over the true airspeed of 220 knots. Next, we align the heading of 180 degrees true on the inner scale with the true heading index on the outer scale. We always apply the drift from heading to track, and we can see that the track of 171 degrees true corresponds to 9 degrees left on the outer drift scale. So we make a mark where the vertical 9 degrees left drift line intersects the ground speed of 200 knots. Now we rotate the inner scale to put the wind mark on the centre line beneath the true airspeed centre dot. The wind direction of 235 degrees true can now be read beneath the true heading index. We can see that the wind mark is over the 180 knots ground speed line, which is 40 knots down from the centre dot. Therefore, the wind vector is 235 degrees at 40 knots. Here is an example where we need to calculate one of the components before we can calculate the wind vector. We need to calculate the ground speed and can see from the question that we have travelled 47.5 miles in 15 minutes. If we align the time of 15 minutes on the inner scale with the distance of 47.5 miles on the outer scale, then we can read off the ground speed on the outer scale against the 1 in 60 black triangle index on the inner scale, 190 knots. Now that we have the ground speed, we can turn over to the low speed side of the sliding wind scale and place the centre dot over the true airspeed of 175 knots. Next, we align the heading, 085 degrees magnetic, on the inner scale with the true heading index on the outer scale. Then, working, as always, from heading to track, we can obtain the drift of 5 degrees right. Make a wind mark on the slide, where the 5-degree right drift line intersects the ground speed of 190 knots. Now, as before, rotate the inner scale to put the wind mark on the centre line below the centre dot true airspeed and read off the wind direction, 313 degrees magnetic under the true heading index. Count down from the centre dot over 175 knots to the wind mark over 153 knots, a difference of 22 knots. We now have our wind vector of 313 degrees magnetic at 22 knots. Now we must apply the magnetic variation to calculate the true wind. We know that the magnetic variation is 10 degrees west, which means that the magnetic heading is best, that is to say, more than the true heading by 10 degrees. So we subtract 10 degrees from the magnetic heading to give a true heading of 303 degrees. So we have a wind vector of 303 degrees true at 22 knots. Sometimes we need to plot more than one drift line to calculate the wind vector, as seen in this example. In this example, we first need to calculate the inbound drift. Using the low speed side of the sliding wind scale, we position the centre dot over the true airspeed of 180 knots and align the inbound heading of 015 degrees magnetic on the inner scale with the true heading index. We are tracking the 200 radial inbound, which means our track is the reciprocal of this, namely 020 degrees magnetic. Working, as usual, from heading to track, we can see that we have 5 degrees right drift on the inbound leg. We draw a line down the 5 degrees right drift line. Now we calculate the drift for the leg outbound from the Bravo Charlie November. We align the heading of 075 degrees magnetic on the inner scale with the true heading index, and working from heading to track, we can see that we have 5 degrees left drift on this leg. So we draw a line down the 5 degrees left drift line to intersect our first line. Now rotate the inner disc so that the point of intersection is on the centre line beneath the centre dot, which is over the true airspeed. Read the wind direction, 224 degrees magnetic, at the true heading index. Now count down from the centre dot over the true airspeed to the wind mark over 142 knots, a countdown of 38 knots. The wind vector is therefore 224 degrees magnetic at 38 knots. However, the wind direction is in degrees magnetic, and we need to apply the magnetic variation to calculate the true wind. The magnetic variation is 16 degrees east, and we say variation east magnetic least. So the true heading is more than the magnetic heading by 16 degrees. The wind vector is therefore 240 degrees true at 38 knots. The actual wind we encounter on the leg between 2 points is rarely the same as the forecast wind we use to plan our heading to fly. As a result, at our scheduled checkpoints along track, we may find ourselves a certain distance off track, having encountered a track error angle. This section will show you how to use the CRP-5 to calculate the adjustment we need to make our heading to fly directly from our checkpoint to our destination. If we simply adjusted our heading by the track error angle alone, we would simply parallel our original desired track. We must also calculate the closing angle, which is the track error angle measured from the destination to the checkpoint. The total adjustment to the original heading we require is obtained by adding the track error angle and the closing angle together. In this first example, we are flying between 2 waypoints 80 nautical miles apart and find that we are 3 nautical miles left of track after 45 nautical miles. To find the initial track error angle, we align the distance off track, 3 nautical miles, on the outer scale with the distance along track, 45 nautical miles, on the inner scale. We can now read off the track error angle of 4 degrees against the 1 in 60 black triangle. We were left of track, so our initial track error angle was 4 degrees left. Now let's look at a closing angle calculation. We are flying between two waypoints 70 nautical miles apart, and after 30 nautical miles, we find we are 4 nautical miles right of track. Again, we align our distance off track, 4 nautical miles, on the outer scale, with our distance along track on the inner scale. This time, however, the distance along track is the remaining distance to go to our destination, 40 nautical miles. We now read off the value of the closing angle on the outer scale, opposite the 1 in 60 index black triangle on the inner scale. The closing angle in this case is 6 degrees. We will now look at calculating a revision to our original heading. Our two airports are 105 nautical miles apart, and we have been heading 105 degrees true. After 35 miles, we are 3.5 nautical miles right of track. First, we calculate the track error angle by aligning our distance off track, 3.5 nautical miles, on the outer scale, with our distance along track, 35 miles, on the inner scale. We then read off the track error angle of 6 degrees against the 1 in 60 index black triangle. Now for the closing angle. We align the distance off track, 3.5 nautical miles, on the outer scale, with the distance from our checkpoint to the final destination, 70 nautical miles. Reading the outer scale opposite the 1 in 60 index black triangle on the inner scale, we get a closing angle of 3 degrees. Adding the track angle error and closing angle together, we get a total heading adjustment of 9 degrees. The track error was to the right, so we need to turn left onto a revised heading of 096 degrees true. The calculator side of the CRP-5 can be used to find approximate rates of descent on given glide path angles or gradients. We use the 1 in 60 index black triangle as an index for glide paths and the red arrow as an index for gradients. It is worth noting that glide paths are measured in degrees, whilst gradients are measured in percentages. We can work out the rate of descent required to fly a 3.2 degree glide path at 140 knots by first aligning the 1 in 60 index black triangle on the inner scale with the glide path angle of 3.2 on the outer scale. Then we look up the ground speed, 140 knots, on the inner scale and read off the approximate rate of descent, 745 feet per minute, on the outer scale. And to work out the rate of descent required to fly down a 6% gradient at 200 knots, we first align the red arrow with the gradient of 6 on the outer scale. Then look up the ground speed of 200 knots on the inner scale and read off the approximate rate of descent, 1200 feet per minute, on the outer scale. The calculator side of the CRP-5 can also be used to find heights and distances from glide path angles or gradients. As before, we use the 1 in 60 index black triangle as an index for glide paths and the red arrow as an index for gradients. In this example, we wish to find out how high an aircraft is above airfield level if it is 8.4 nautical miles from touchdown on a 3.3 degree glide path. First, we convert nautical miles to feet by lining up 8.4 on the inner scale with the nautical mile index on the outer scale and reading off the value of 51,000 feet on the inner scale against the feet index on the outer scale. Now we line up the 1 in 60 index black triangle on the inner scale with the glide path angle, 3.3, on the outer scale. Looking up 51,000 feet on the inner scale, we can now read off the approximate height of 2,800 feet on the outer scale. In this case, we know the aircraft is on a 6% gradient descent and is at 3,400 feet, and we wish to find its approximate distance from touchdown. We align the red arrow with the gradient, 6, on the outer scale, and then look up 3,400 on the outer scale. On the inner scale, we read off 56,500 feet. To convert this to nautical miles, we align the 56,500 on the inner scale with the feet index on the outer scale, and moving the nautical mile index on the outer scale, we read off the distance of 9.3 nautical miles on the inner scale. The CRP-5 can also be used to calculate the time needed to descend from one altitude to another, and also the distance covered in such a descent. These calculations are performed in 2 steps. What rate of descent is required to descend from flight level 320 to flight level 80 over a distance of 80 nautical miles at a ground speed of 320 knots? First, we calculate how long it will take to travel the 80 miles. Placing the 1 in 60 index black triangle on the inner scale against the ground speed of 320 knots on the outer scale, we look up 80 miles on the outer scale and read off 15 minutes on the inner scale. The total descent is 24,000 feet. We divide 24,000 by 15 minutes by aligning 15 on the inner scale with 24,000 on the outer scale and reading the answer against the red arrow on the inner scale. In this case, the answer is a required rate of descent of 1,600 feet per minute. In this example, we know the rate of descent and the ground speed, and need to find the distance covered during the descent. First, we need to work out the time for the descent. Align the red arrow on the inner scale with the rate of descent, 1,280 feet per minute, on the outer scale. Now look up the total descent, 28,000 feet, on the outer scale, and read off the time, 21.8 minutes, on the inner scale. Aligning the 1 in 60 index black triangle on the inner scale with the ground speed of 440 knots on the outer scale, we can look up 21.8 minutes on the inner scale and get our distance of 160 nautical miles on the outer scale. And in this last example, we know the rate of descent and the distance covered during the descent, and we need to work out the ground speed. Setting the rate of descent, 1,400 feet per minute, against the red arrow on the inner scale, we look up our total descent, 16,000 feet, on the outer scale, and read the time taken of 11.4 minutes on the inner scale. Now, if we align this time on the inner scale with the distance of 40 nautical miles on the outer scale, we can read the ground speed, 210 knots, on the outer scale opposite the 1 in 60 index black triangle on the inner scale.